to lecture number 3 of this course, Database System Principles. Today, we're going to talk about a data structure. In fact, this is the beginning of a series of lectures devoted to data structure and indexing. We're going to start with B-trees today. So the B-tree is by far the most important data structure in a database system. And in the next lecture, we're going to talk about hash indexes. So hash indexes are also quite useful in database systems, but not as useful as the B-tree. Okay. All right. So let's look at this data structure together today. So what is a data structure? Well, I think most of you have taken this course, data structures, or some course, very related to data structures. If I have to give a one-sentence summary of all the data structures, it will have to be, this is a way to organize your data in order to support certain operations efficiently. Okay, so you have to remember we should always be talking about operations. Otherwise, it's quite meaningless to talk about data structures. Okay, if you just want to store your data, I mean, you can do that with an array, linked list, but you don't really need a data structure, right? But if you really ask yourself, what's the real reason for you to, organize data in the way they are in a data structure, it has to be for additional reasons. And typically, very typically, the reason is to support certain queries or certain operations, maybe update operations efficiently. The B-tree is basically utilized to answer certain types of queries efficiently. And let's first define those queries so that we can understand what is the target of the design. So to start everything, we have to be clear about what is the input. So here, for today's lecture, I'm gonna, for most part, until the very end, okay, for most part of today's lecture, I'll be basically assuming that the set is a set of integers. And here, the first blue box defines what it means by a predecessor query. So you see this predecessor query is issued on the input. And this query will have to specify a search value. So the search value Q, and it returns the, as you can see here, the largest integer in your input, but this integer cannot exceed Q. Okay, so this is called the predecessor. Well, this might be too mathematical, so let's go into this example. Say I have this set S here. So I have sorted these numbers. I've sorted these numbers in ascending order just for your convenience. So if you have Q being 35, as you can see, 35 would have been at this position, right? So the predecessor is 27. So this is right the number. Sorry, the number right before this is 35. Okay, so that's 27. However, you have to be a little bit more careful if the search value itself is in the set S. So for example, 38, if I say, hey, what is the predecessor of 38? And then you should tell me, hey, that's 38, okay, not 27. Okay. So going back to the definition, you can see this is the meaning of the largest integer X, in the set. However, this X must satisfy this condition saying the X does not exceed Q. Okay, so this is called the predecessor of Q. The opposite of this is called the successor of Q. Say, let's look at the example directly. Say if I still give you 35, okay, so 35 is here, and then a successor will be 38, so this is the number right next to it. Once again, you got to be a bit more careful if Q itself is in the set S. So if 38 is the search value, and then a successor is 38 itself. Okay. All right, so these are two queries that can be supported efficiently by the B tree. And there's one more we're going to talk about. Here, once again, S is the input set. That's a set of integers. And we have a range query here. So a range query specifies an interval. Okay, so it's not just a single search value anymore, and it's an interval. Okay, and what you want is to report everything in the input set that falls into your search interval. Okay, so that's called a range query. Again, I think it will be easier if we look at an example here. Say this is the same input as before, and this is the query. As you can see, it's an interval, and essentially we want to find everything that's from 35 to 49. Okay, so everything in here. As you can see, the output consists of these three numbers. Okay. Nice. All right. So these are three types of queries that can be supported by the B tree. As you'll see, predecessor and successor, they are symmetric. So essentially, I would say they constitute just one type of queries. So in essence, there are only two types of queries that we're going to be talking about, say predecessor and range query. Okay. In addition, a B tree is fully dynamic. Okay, fully dynamic. What that means is it's able to support both insertions and also deletions. Okay, so what insertion means is, I give you a new integer, and you have to put it into the set S, and deletion says, okay, I tell you which integer I like to remove, and then you have to do that for me. Okay. So as you can see, this data structure is pretty powerful. It's able to support all these operations efficiently. How efficiently? Well, we won't be able to talk about that at this point, and we will first introduce the data structure and understand a few basic properties about it. And then in the end, when we get there, I will analyze the performance for you. Okay. All right, so now let's start with the basic definitions and properties. So once again, this is the input this is a set of n integers. Wow, this is the definition. It looks scary. There are a lot of words. There are a lot of words in the definition. Okay, which is why we will not look at it immediately. Let's look into an example to get some intuition first. Okay, so here this is the set, and we want to define a B tree over it. So this is what a B tree would look like. So let's look into the components of this B tree bit by bit, okay? So this B tree, which I denote by T, okay, this T, has a parameter, okay? So this parameter is small b, okay? So in this case, this small b is set to 3. And what's the meaning of this small b? The meaning is that, in a no, you can fit at most 3 numbers. Okay, so this would be a very simple statement about this b. Okay, and there's more to it. I'm gonna talk about that later. But you can basically understand this b as saying, how many numbers, how many entries, how many elements you can put into one node. Okay, so this applies to both leaf nodes and also internal nodes. Okay, but as I said, this b also tells us more things, which I'm going to talk about later. Okay, so so here is the tree. Some standard terminology first. As you can see, we have many nodes, right? So I have given them some names. This node is called Z1, and this one Z2, so on and so forth. And also here I have U1 for this node, U2 for this one, and U3, right? So you can see on purpose, I chose different letters for the nodes at this level. And also I choose another letter for the nodes at other levels. So what's the difference? Well, I guess some of you have already realized the difference. So here, this is the leaf level. Okay, so this is the leaf level, and these are the non-leaf levels. Okay, and oftentimes we use the word internal level to represent to refer to non-leaf levels, right? Just a fancier term for non-leaf levels, but it will be perfectly fine if you say non-leaf levels. Okay, so I'll go with internal levels by default. Okay, so look, these are the leaf levels, and the nodes here, they are the leaf nodes. Okay, they don't have children, right? In general, in a tree, if you have a node that doesn't have any children, and then this one is a leaf. Okay? Otherwise, it's an internal node. So U1, U2, U3, they are internal nodes. Okay. All right, so now let's look into the leaf nodes together. Okay, the leaf nodes. So here you can see there is one correspondence between the elements in the set S and also the elements in the leaves. Okay, so for your convenience, I have already sorted the elements in S in ascending order. And if you look at the ordering here at the leaf level, you can see the elements are also sorted. Okay. And later you will realize this is not a coincidence. This is a nice property of the B tree. Okay. All right. I was saying there's one correspondence between the elements in the set S and also the entries, elements in the leaves. Okay. I use the word entry. I also use the word element, and both terms are standard terms to refer to things inside a node. Okay, so you could say 5 is an entry. You could also say 5 is an element. Okay. So one correspondence. Okay, good. Well, now let's move on to the internal nodes. Okay, U1 and U2 and U3. You can see we also have some numbers inside the nodes, right? So this is a moment that could confuse some students. Some students would say, hey, for example, 5, why do we have to store it 3 times, right? And maybe if you look at 12, you can see that, it's stored only once in the whole tree. So, that's not fair. Why this special treatment for 5? Okay. Yeah, absolutely. This is a fair question. So let's look deeper into the tree. Okay. So the elements in the internal levels are actually for purposes different from the elements at the leaf level. So for the elements at the leaf level, they are for storage, which means this is really the place where the elements are actually stored. Okay. And for this reason, we call the entries in the leaf nodes, we call them data elements. Okay, so next time when you hear me say data element, then I'm talking about an entry inside a leaf node. This entry is definitely in the input set. Okay, so that's for the leaf level. So how about the internal levels? Well, you see some elements being duplicated at the internal levels, but the purpose is not to store those elements. Okay, so once again, if the elements are stored at a leaf level, okay, so the purpose for the leaf level is storage, but the elements stored at the internal levels are for the purpose of directing search processors. Okay, so this is going to be even clearer later, but here you can take my word for it. So as I said, the elements at the internal levels, the purpose is for directing search when you answer queries, when you support operations. Okay. So for this reason, we will give a different name to every element at the internal levels. So we'll refer to them as the routing elements. Okay. So I think this makes it really explicit from this name, right? You can see their purposes are for routing, for directing. They're just like road signs. Okay, road signs that direct the traffic. Okay. All right, but there were more secrets to it. Now let's look at this internal node. You can see U2 has two child nodes, right? So Z1 is one child node and Z2 is the other. And you can see two child nodes and two routing elements. Okay. Well, in general, this is always the case. If you look at an internal node, you count how many routing elements it has. It's always equivalent to the number of child nodes of this internal node. Okay. Indeed, there's one correspondence. This is 5 is for leaf node Z1, and the 16 is for Z2. Okay. Sometimes you will hear me say, hey, this Z1 is the child of this routing element 5. This is perfectly clear because there's one correspondence, as I said, right? So there's no room for ambiguity. And similarly, I would say Z2 is the child of this routing element 16, and so on and so forth. Okay, so now let's look at this 5, right? Just now I said, hey, some special treatment for 5, and 5 gets duplicated at no U2. Why 5? Why not 12? Okay, well, 5 gets this special treatment because it is special. Okay, so how is this special? Look, as I said, this 5 is for Z1. Okay, now let me ask you, inside Z1, which one is the smallest element? Okay, yeah, it is 5. Okay, it is 5. So now this is a very important property of the B tree. The routing element, each routing element, okay, is very carefully chosen. Okay, so this routing element is supposed to be the smallest routing element in the child node. Okay, so that's why you want to put 5 here. Okay, so this is important, and if you don't do this, and then you could run into a lot of errors when you support operations. Okay, so you can see this is true everywhere. The 16, this is the smallest of the child. 44, this is the smallest in the child. 81, smallest in the child, and so on. Okay. Hey, by the way, this is true everywhere. If you look at U1, right? Same thing. Same thing applies. So first of all, 2 routing elements. That's because you have 2 children there. So you got U2 and U3. So why is 5 duplicated again? Because 5 is the smallest number in U2. Okay, when I said number, I try not to use the word element, but I could, except that I should have said routing element, right? And 44 is the smallest number or routing element in U3. Okay, so as you can see, we play by this rule everywhere in the tree. Okay. So now we are getting a better picture of the B tree. Let's continue to talk about some advanced parts of the definition. Okay. Well, now let's look at this 12 here. Okay, so you can see this 12 gets placed here rather than anywhere else. Well, there is some rule behind this. Okay, in the B tree, if you look at, let's say, U2, as you know, 5 and 16. So the 16 represents the smallest number in Z2. So you already know that, right? So 5 is the smallest in Z1. However, what I have not mentioned is that, this 12, which is in the child node of this Z1, right? So this 12 here, this 12 is strictly less than the 16. Okay. Remember what I said before about the row sign, about the routing element, the purpose, the routing purpose. Now you can start to feel that we are already benefiting from this these routing elements, because you got this 16, right? Let's say you are standing here, you have not reached any child node yet, so you're standing here in 516, right? And you can already tell yourself that, hey, if you're looking for something that's at least 16, and then you should make a right turn here, okay? Because as I said, the B tree guarantees this property that everything under 5, okay, inside the child node of 5 will have to be strictly less than 16. Okay, in other words, 5 will have to be in there because of the definition of the routing element. This has to be the smallest in the child. So, everything will be at least 5. Okay, 5 is there. And you can also know that, everything inside Z1 will definitely be between 5 and definitely strictly less than 16. Okay. Same thing everywhere. Say you are standing at U3 and you have not descended to any of the child nodes. And if you're just standing here and if you ask yourself, hey, what can you say about the range of numbers in the child node of 44? And then you know that, those numbers will have to be at least 44, but strictly less than 81. Okay. Same thing if you look at the child node of 81, what can you say about them? The numbers there, what you can say is that, they will have to be at least 81, but strictly less than 92. Okay. So let's go to this U1. Same thing again. This is the root. Okay, so you just open the root, but you haven't accessed a lot of information yet, right? Just the root. However, at this point, you can already say a lot of things about the subtrees. If I say what is the subtree of 5, this is the subtree, right? It has more than one node, right? If I say what is the child node of this 5, hey, by the way, this is the child node, right? But if I say what is the subtree of this 5, you should say, hey, this is the subtree of 5. What's the subtree of 44? This is the subtree of 44. Anyway, so what can you say about the numbers stored in the subtree of 5? You know that 5 will be the smallest, definitely the smallest number in the subtree, because that's how things are defined, right? And all the numbers will have to be strictly less than 44. Okay, so that's another thing you can say. Okay, so 44. What can you say about the other subtree? As you can see, there's no more routing element here, so you can think about it as infinity. So what you know is everything will have to be at least 44, but can be arbitrarily large. Okay. So that's the ordering property of the B tree. So you can see the B tree. The B tree is in fact maintaining an order on the elements. Except that the ordering is not stored in an array. Instead, it is stored inside a tree. So why not an array? This would be a great question. And later on, we have to do updates. Okay, so if you store everything in an array, and then if I have to insert something into the array, and then it would take you a lot of time to move the elements around just to make room for this new element. Anyway, so this array would be a great idea if everything's static, but if you have to support insertions and deletions as we do in database systems, and then array is not the way to go. Okay. All right. Lots of stuff, huh? We're still talking about the definition. And one more thing to talk about. So as I said, there's more to this value B, right? This parameter B. So this parameter B says something else. I just talked about the upper bound side. So I said this B tells you, in every node you can have at most three entries. Okay, three entries. Okay. So as you can see, every node has at most three entries, right? Um, so this is from the upper bound side. But what I did not tell you is that this B also implies that every node will have to have at least uh, B by 2 entries. Okay, at least. Okay. Well, of course, in this case, B is an odd number, and then you will say B by 2, that's 1.5, right? So what do I mean by larger than or equal to 1.5? Is that a mistake? No, it's not a mistake. So larger than or equal to 1.5 means you have to have at least two entries. Okay, so this is the case everywhere, as you can see here. Every node has at least two entries. Okay, so if B is 10, and then it means every node would need to have at least five entries. You get the idea. Okay. Well, there's only one node. There's only one node that can have a little bit special treatment regarding this rule. And the node is the root. Okay, the root will need to have at least two entries. Okay, which means it needs to have at least two child nodes, and it will still have to abide by the upper bound, which means it can have at most B elements, B child nodes, right? However, it is allowed to go below B by 2. Okay, so of course, when B is 3, you don't really see the difference because B by 3 is already basically saying, the lower bound is 2, but consider B taking a higher value, say B is 10, and then D by 2 will be 5, right? But so in this case, every other node will need to have at least 5 entries, but the root is allowed to have as few as just 2 entries. Okay. Why the case? Well, we'll see this when we talk about insertion algorithms. Okay. Okay, so as I said, a lot of stuff, and I hope that has been clear. But remember, this is just an example. This is no replacement of the formal definition. Okay, so if we want to have rigorous understanding, we still have to go through the definition. But hopefully, the example has made it easier for you. Okay, now let's see. So here I have this whole definition, and the purpose is to show you that this is a mathematical concept, and there should be no room for ambiguity. Okay, math is rigorous in the sense that you have no alternative interpretation of the thing that's being defined here. Okay, so basically anything that fits into this definition gets to be called a B tree. Okay, so a B tree created on this particular input, and a B tree that is parameterized by this value B. Okay, and so this B has to satisfy this condition. It needs to be at least 3. So this is a tree. Okay, so I assume everybody knows what a tree is. Um, this is something rudimentary, and you should have taken a course about that. So I'll be using tree terminology directly without defining them. Anyway, so this tree needs to satisfy 4 conditions, and any tree satisfying these 4 conditions is a B tree. Okay. So what are these conditions? First of all, you can see every element of S. Okay, every element of S is stored in one leaf of T. Okay, so this is uh, this is what I said before, right? I said there is one-one correspondence between the input elements and the entries in the leaves, right? So this is basically what it says. And the second condition says all the leaves, all the leaf nodes are at the same level. Let's look at the example again. In D, as you can see, all the nodes are at level 2. By the way, this is level 0, this is level 1, and this is level 2. Okay. All right, so they're at the same level. So if T has more than one level, so there's at least 2 levels, right? And then every leaf node will have to store between B over 2 and B elements. Okay, so this B over 2 to B, basically, they're talking about this lower bound and upper bound that I said before. So when B is 3, for example, then basically says every leaf will need to have at least 2 entries and at most 3 entries. Okay, and the elements in the leaves are called the data elements. Okay, there is this mysterious if condition here. Okay, and let's talk a little bit about this if condition. If this if condition does not hold, it means T has how many levels? Has just one level, okay? But how can a tree have just one level? Well, the tree has only one level if it has nothing but just one node, right? So this node is the root, and at the same time, it's also the leaf. Okay, so this is a very, very, very special case where, you have basically very small number of integers in the input set S. Okay, you cannot even have enough integers to make a tree with 2 nodes, right? So in that case, you are allowed to have as few elements in this node because that's all you have in the input set, right? So basically saying this is a very special case that can be treated separately. But other than this special case, this lower bound and upper bound constraints will have to apply. Okay. So that is the second condition. Basically, the second condition governs the leaf nodes. Okay. The next condition governs the internal nodes, right? So here it says, okay, if you look at an internal node, and then there are also some size constraints. So typically, this node will need to have at least B by 2 elements and at most B elements, right? As I said, the root is the only node that does not really have to fully abide by this rule, and it can have a little bit of special treatment. So the lower bound is 2, regardless of the value of B. Okay, so so once again, when B is 3, and then B by 2 essentially says you need to have at least 2, but keep in mind that B can be much higher than 3, right? So regardless of the value of B, the root is required to have at least 2 channels. Okay, good. Well, so far we have not defined anything about routing elements, and that cannot be correct. So condition 4 is fixing this. So this is saying, well, if you look at an internal node here, and let's say we list out their routing elements from left to right as V1, V2 to VF, for some F. Okay, by the way, this F is often referred to as the fan out of this internal node. But anyway, so V1, V2 to VF. Okay. Now remember, this is a child node. Okay, child node, right? But inside this V, inside this U, we will have to store some routing elements. Okay, so this routing element goes like this: R1, R2 to RF. Okay, so R1 is for V1 and R2 is for V2, etc., etc. Okay. Now, this routing element, they will have to be carefully chosen in the following sense. Okay, so if you look at, for example, V2, and you look at this routing element, I don't know, Ri for some I, that is to the right of 2. So that's bigger than 2. Okay. So basically, this says everything in here, all the numbers that are stored in the subtree, okay, will have to be strictly less than Ri. Okay. So, R1 is less than R2 and R2 is less than R3, etc., right? So here, this R2, you can see this, it's a subtree is to the left of Ri. Still remember what I said about the row sign, right? So everything in this subtree will have to be strictly less than this Ri. So to illustrate this property, so if you look at 5 and 44, everything in this subtree, right? Everything, I'm talking about everything, okay? This includes the data elements and also the routing elements, everything, okay, will have to be strictly less than 44. Okay, so this is an ordering property. So this is what it says here. Okay, so everything in this subtree will have to be strictly less than this. Okay, so this is about the second bullet. I don't know if I talked about the first bullet, maybe not, but this is something easy to understand. So this R1 will have to be the smallest data element in the entire subtree. Okay, so if you look at this 5, right? So this 5, the entire subtree is this. So this 5 is indeed the smallest element in the entire subtree. Okay, so this 44, this is indeed the smallest data element in the entire subtree. Okay, so this is what the property is saying. Okay. Well, regarding this requirement, there were 2 ways to define it. In fact, when I talked about this example, my definition was that this 5 will have to be the smallest element, in this case, routing element in this child, right? And again, this 5 will have to be the smallest in this leaf node. Well, these 2 definitions are actually equivalent. The definition about the routing element is actually equivalent. Why? Because, if 5 is the smallest in this child, right? And again, this 5 is the smallest in this child. So there is this recursive definition. And this definition basically implies that this 5 will have to be the smallest of the entire subtree. There's no way around it, okay? All right. So that is the definition of a B tree. This is a long definition. And hopefully now you have a good understanding about it. Okay. So remember, we are talking about disks. This is a disk-oriented data structure. And every node of the B tree occupies a disk block. Okay. So this is the reason why the value B, this value B here, in general, can be very large. Okay, because it really depends on the block size. Okay, so still remember the block size. This is the number of bytes inside a block, right? Let's say 4,000 for 4 KB. That would be 4096. So lambda can be very big, and if you think about an integer, it takes 4 bytes or 8 bytes to store an integer, right? So each block can store a lot of integers, right? So this value of B can be very large. It's proportional to this lambda. Okay. So here is an example. So let's say the block size is 4 KB, and we use 4 bytes to store an integer. So a data element or routing element would take 4 bytes. But if you look at this example, you will see besides just an integer, we also have to store a pointer, right? So if you also consider that, a pointer, let's say we use 8 bytes to represent an address, and then every element, in particular, every routing element would have to get associated with, every routing element would have to store 12 bytes, okay? Some of you would say, well, hey, how about this data element? Well, you will see when we deploy this B tree in the database system, every routing element will also store a pointer. Okay. However, this is going to be a pointer that points to a position in some relation, okay, in some table. Okay. So now remember, in the end, we're talking about tuples, right? And this 12 is just one value of the tuples. So this pointer that I'm indicating here refers to that tuple. Anyway, this is something we'll see in 2 lectures after two lectures down the road. But just so you know, you might also have to store a pointer for each data element. So that would make the number of bytes needed to represent an element 12. Okay. And so if you have 4096 bytes, how many elements can you fit into one disk block? The answer would be 341. So this gives you an idea how big this B can be. Okay, 341. Okay, so that would be a typical value in practice. Okay, good. So now we can have a some solid understanding about the space consumption and also the height of a B tree. So let's say the input set S has n integers, and this B is the maximum capacity, right? Okay, so the theorem says this B tree will have at the order of n over B nodes, at the order, okay? So you see this big O here. Well, in the data structure course, you should have learned this, but I guess maybe you don't use it a lot. So what this big O means is that, there is a constant that we're hiding here. So this constant, I don't know, it could be 2, it could be 3, for example, but there's a constant that we're hiding there. So this T has no more than a certain constant number of nodes. So this is what it means. Okay, so there is certain constant, and this constant multiplied with this n over b will give you an upper bound. It's a guarantee, right? So it's an upper bound, cannot be more than that. So there's upper bound on the number of nodes you can have. Okay, so this is what it means by the big O. So every time you see big O, 2 things should come to mind. The first one is there is a constant that is hidden. The second is that this big O essentially is saying less than or equal to. Okay, so it's an upper bound. So you can think about it as less than or equal to C, some constant. And we don't bother to talk about that constant. So that constant times n over b. Okay, so this is the order of magnitude, right? So we want to understand how this thing changes when the parameters change, right? So n is a parameter and b is a parameter, but this constant never changes. Okay, it doesn't really matter what the parameters are, and the same constant should be sitting here. Okay, otherwise you cannot hide it. Okay. So anyway, this is telling us that the tree uses n over b nodes at the order of n over b nodes. And also the height of the tree is log base b of n. Okay. So note that the base here is b. Okay. This is actually much smaller than log n. Okay. So this is equivalent to log n over log b, right? And remember, b is a large number, let's say about 300. So log b can be, pretty big, right? So this is significantly less than log n. Okay. So I'm not going to formally prove the theorem in this video, but let's look at an example to get some understanding how the theorem is proved. Okay. So here you can see we have 1 million integers in the input set, and let's say we set the value of b to this number, and this number was obtained on the previous slide. All right, so you can see from this example, the value of b is chosen to be more than 300. So here, let's analyze bullet by bullet. So first of all, the first bullet says because of the constraint, so every node, except for the root, okay, so except for just one node, okay, every node. So this is not very, very accurate. I should have said, sorry, I should have said every non-root node, say non-root, okay. So every non-root node has at least how many elements? So you know it has to be at least be over 2, right? So here we're taking the ceiling because we want an integer, and therefore it's 171. Very good. So how many leaves can we have? Well, you know, every leaf node must accommodate at least 171 elements in your set, right? Cannot be less than that. So you cannot have this number of leaf nodes. Okay, so if you calculate this, this tells you even in the worst case, you cannot have more than this number of leaf nodes. Okay, you can have way less. You can have way less because this is a basically this is the worst case situation where every leaf stores strictly the smallest number of the smallest permissible number of elements, right? So this is 5a, 4a. So if I say what is the best situation, and then it's going to be n divided by 341, right? So that would be the best situation. So if you do that, it's about twice lower. Anyway, so this is the maximum number of leaf nodes you can have at the leaf level. So let's look at level 1. Okay, so you use that number. So this number basically tells you what is the largest, okay, what is the largest number of routing elements you can have at level 1. Okay. By the way, still remember how we order the levels? This is ordered. This is level 0. This is level 1 and level 2, right? So you can see the number of routing elements at level 1 is precisely the number of nodes at level 2, right? So that's why you can do this translation. If you get an upper bound on how many nodes you can have at the leaf level, at the leaf level, and then you can get an upper bound on the number of routing elements at the previous level. Okay, so here I am counting the levels in an opposite manner. Actually, this is another way to count the levels. So you can also say the leaf level is level 0, and then you add one more to each level up. Okay, so I should have used this counting system rather than this counting system. Okay, so both systems are there, but when I was writing the slides, I was actually using the other one. Okay, so let's just switch to the other counting system. Anyway, so here from what I said before, as you know, this 5a 4a tells you you can have at most this number of routing elements at level 1. Okay. And so how many level 1 nodes can you have at this level? Every level 1 node will have to accommodate at least 171, right? So you can see we're applying the worst case estimates for both the numerator and also the denominator here. So for the numerator, at most this number. For the denominator, at least this number, and therefore, we have an upper bound on the number of level 1 nodes. So that's just 34. Okay. All right. So this further tells us, at level 2, you can have at most 34 routing elements. Okay, and therefore you can have just one root at that level, and that's it. Okay. So this is already the worst case situation. So even in this worst case situation, there cannot be too many levels. There are only 3 levels. And how many nodes can you have in the entire tree? Just add up all these numbers. So you get 5, 8, 8, 3. Okay. So I can tell you that this B is, this is something I said before, right? So this B is at the order of uh, lambda. Okay, as you can see, I'm using big theta here. Again, some of you may not like this big, may not be familiar with asymptotic analysis. So basically, this big theta says, B and lambda, they are within a constant factor of each other. So for example, B could be lambda divided by 12, something like that, okay? So I can tell you this N over B is essentially N over lambda, okay? N over lambda, okay? So this is the space consumption of the B tree, okay? All right, now let's go further. You already know what a B tree is, so I think it should be fairly easy to get convinced that the B tree is ordered, has a total order on the leaves, right? So you can see Z1, Z2, Z3, Z4, Z5. If you enumerate these leaf nodes in this order, you can see that the data elements inside them are clearly in ascending order. Okay, so this total order is quite important to us. This echoes the statement I said earlier that the B tree essentially is created on some total order, right? So this is exactly the order that I was talking about, okay? All right, now this order further leads us to a very related, uh, variation of the B tree, and this is called the B plus tree. So the B plus tree is just a B tree. It also takes a parameter, this B. So it's just a B tree parameterized by this value B. However, there's one difference between the B tree and the B plus tree. So B plus tree will store pointers among the leaves to capture explicitly the total order. So the total order, as I told you before, goes from Z1 to Z5, right? So you can see the leaf nodes constitute a linked list. So Z1 has a pointer to Z2, and so on and so forth. So what's the benefit of these pointers? The benefit is that when you are at Z1, for example, you can directly jump to Z2. Okay, you don't have to do any search through the internal levels anymore. You can just go from Z1 to Z2 directly. And likewise, another example, if you're already at Z3, and then you can jump to Z4 directly, okay? This is going to be helpful to us when we try to answer range queries. This is something we're going to talk about very shortly. So this is what the B plus tree says. Okay, some students would get creative here, saying, okay, so how come the pointers are one direction, in one direction, right? Can we make it bidirectional, which means can we store a back pointer from Z2 to Z1, okay, Z3 to Z2, and so on? Well, you surely can, okay, no problem. Just go for it. You can definitely use your creativity to store whatever you consider useful in the tree. Okay, but the B plus tree does not really require that. Okay. Well, an interesting remark here. People today they already get really used to these two variations so much so that they tend to use the terms interchangeably. Okay, so today the line between the B tree and the B plus tree is really, really fuzzy. In fact, when people say B trees, they don't realize they're actually talking about B plus trees. Okay. Um, yes. So in this course, I might slip out the word B tree incorrectly. Sometimes I might want to say B plus tree. I also have this issue, just so you know. Okay, but the line between the two structures is really, really fuzzy already. Okay. Okay, so let's talk about query processing. Okay, so we already understand what a B tree is, and now let's see how we can use it to do some good stuff. Okay, so starting with predecessor search, right? By the way, this is the algorithm, but let's look at an example first, and then we go back to the algorithm. Okay, so here we have the tree that we've seen before, and we want to find a predecessor of 85. Okay, so as a human being, you know the predecessor is 81, but the thing is, how would an algorithm be able to figure this out by resorting to a B tree? Okay, so the search algorithm always starts from the root. So here you open the root. Now remember that the node is on a disk block. Is stored in a disk block, right? So you have to pay $1. You have to pay 10 milliseconds to perform an I/O, so that you can get this block into the main memory. In the main memory, you can take a look at it, and then you see two routing elements, 5 and 44. Okay. So now you have to make a decision. You have to decide to descend to U2 or descend to U3. By the way, the address of U2 is placed here. So by looking at 5, you also see the address of U2. So if you want to go to U2, you can, no problem, right? And similarly, you also have the address of U3. But the thing is, you don't want to explore any node unnecessarily. So you have to make a decision here. But a little bit of reasoning would guide you toward the right decision, right? So here you reason as follows. Okay, the predecessor of 85 is supposed to be smaller than or equal to 85, but it has to be the largest number that satisfies this condition, right? So you talk to yourself like this. You see, 44 is already less than or equal to 85. And we know 44 is the smallest data element in the subtree of 44. So this means 44 is indeed in the set. It's indeed in the input set. So 44 is already less than or equal to 85, and therefore anything that's strictly less than 44 cannot be the predecessor of 85, because once again, the definition says you want the largest element that is at most 85. Okay, so 44 essentially blocks all the other elements that are less than 44. Okay, none of those elements can even have a chance to become the predecessor of 85. Okay, so this is really nice, because this indicates you can immediately forget about the entire subtree of 5. Okay, you can focus on the subtree of 44. So that tells you to descend to U3 correctly. Okay. All right, so let's do just that. You descend to U3, and you pay another $1 to perform an I/O. Just so you know, every time I say $1, I mean 10 milliseconds. Okay, just $1 vividly tells you how expensive it is. Anyway, you pay $1 to get U3, and you see 44, 81, 92. You apply the same reasoning. You can see 81 basically is the best candidate so far, and it blocks anything that's less than 81 from being the predecessor of 85, right? So this subtree can be immediately eliminated. And so you only have two choices left. You want to go for 81, the child node of 81, or the child node of 92, right? But then a little bit of reasoning would tell you it's a totally wrong idea to go down 92. Why? Because 92 is already the smallest element in the entire subtree, and everything in the entire subtree can only be larger than or equal to 92, and therefore strictly larger than 85, right? So none of them can be your predecessor. Okay, and therefore, there's only one unique choice made here. So you have to go down to the child node of 81, and this is the place where you can find your predecessor, which is 81. Okay, so only here will you be able to conclude that 81 will have to be the predecessor. Okay, even though you have seen 81 here at U3, but this is not the place to make the final decision. Okay. So you access a single path from the root to a leaf, and the leaf is Z4 here. Okay. So how many IOs do we pay? So we pay as many IOs as the height of the trees, right? So if this is level 0, this is level 1, and this is level 2. So we pay 3 IOs. Okay. All right, so now let's go back to the algorithm. This is the formal description of the algorithm. So let's take a good look at it. And I think this example should have made it so much easier for you to understand it, okay? So here you've got this is set S as the input, and this is the tree, and the tree has a parameter B. Now we're talking about a predecessor query, and this is the query value Q, okay? So here I have a little bit of assumption, and I say, okay, let's just assume that the predecessor exists, okay? In this example, if I say, hey, find me the predecessor of 4, and then the predecessor actually does not exist, okay? So basically 4, falls off the basically the range starting from 5, right? So this is actually a very easy case. But anyway, when I describe the algorithm, let's make it a little bit easier so that I don't have to talk about that corner case. So I left this as an assumption, and I said let's just assume that the predecessor exists. Okay. In fact, even if you hate this assumption, you can always insert this minus infinity into the set S as a special element. But even this is unnecessary. Okay, you removing this assumption is actually extremely easy. So I already gave you the hint, right? So you can actually figure this out. There's no predecessor for your queries right at the root, right? You actually just pay $1 and then you get rid of it. Anyway, so assuming that the predecessor exists, you proceed to this algorithm, and this algorithm says you start from the root. Okay, start from the root, and you perform iterations. Okay, so suppose now you are standing at some node U. So if this U is already a leaf, and then you have already reached your destination, so all you have to do is to find the predecessor of your search value among the data elements that you see here. So this is a situation where we have reached Z4. Okay, so here 81, 87, you want to find the predecessor just between the two. So you get 81 there. Anyway, so if U is an internal node, and then you want to look at the routing elements in this internal node, and among those routing elements, you want to find the predecessor. Okay, so this is exactly what we did at U1 and U3, right? So you see, if I say, hey, 85, what is the predecessor of 85 between 5 and 44? Then the answer is 44, right? So that's why we descended to U3. And likewise here, among these three numbers, I said, okay, what is the predecessor of 85? Then you would tell me it's 81, right? So that's why we descended into Z4, okay? So this is the query algorithm. So I think now it should make a lot of sense, right? So the line 4 basically says you want to repeat from line 2 after you have descended to the child. So that's predecessor search. And if you want to look for successors, the algorithm is symmetric. I'm not going to talk about this in detail because I think you can figure that out on your own. But what about the query cost? The query cost is just the height of the tree. And I told you before that the height is log base b of n. This is, once again, better than log n, okay? Because you have this base b here, and b is something large, okay? It cannot be regarded as a small constant, okay? So log base b of n. So that is the IO cost, okay? So this is, if you think about it, this is a very efficient algorithm. I can tell you in practice, the height of a B tree is typically between 3 and 4. Okay, very, very seldom would it go to something like 5, 6. Okay, so you can basically take it for granted that, with 3 or 4 IOs, then you can find a particular value or its predecessor or successor in the data set. Okay. Okay, so that's for predecessor queries and successor queries. Now let's move on to range queries. Okay, so as usual, let's look at an example first. So this time we will resort to the B plus tree. So let's say we're looking at the same example here, and this is the range, okay, from 35 to 65. And again, for human beings, you should be looking at 35 and 63. Okay, so this is what a human being would do, right? Because 81, we don't have to access it, but this is only for human beings. Let me remind you of that. You will see, the algorithm will have to do something extra. Okay. All right. Now let's look at the algorithm. So first of all, this is Q1. All right. So what you want to start with is to find the successor of Q1. So that means you want to find the successor of 35, and the successor is 38. Okay. So the successor is here. How do you find the successor? Easy. We already talked about this. All right. So that's just log base b of n. So that would take you from the root and then all the way down to Z2. Okay, good. But we cannot stop here, right? Because we are supposed to find all the numbers in this range, and therefore we will report everything that we can report in Z2, and then we still have to travel to the right, okay? Because the next leaf might contain elements, might contain integers that we have to report, okay? But the good news is here we can just stride over to the next node, to the next leaf. We don't have to perform any further search because we have this pointer explicitly stored there. We just cross over to the next leaf. So we are at Z3, and then we report everything in Z3. Okay. Now here is a critical question. Do you still have to go to the next leaf, right? Well, as a human being, you will probably say no, because you are seeing things from God's perspective, right? But for an algorithm, it will have to be sure. So the algorithm would reason as follows. Currently, I am at the Z3, and the number that I have seen is 63, the largest number, right? And 63, this is less than 65. So I cannot rule out the possibility that some guy in the next leaf could have something like 64, right? So I still have to travel to the next leaf just to be sure. So this is the reason why the algorithm will still have to do one more step, pay another IO to open Z4. So we also have to access Z4, even though we don't report anything in Z4. Okay. So if I ask you what is the total I/O cost, you should say 5 rather than 4. Okay, so the I/O cost is 5. Okay. Now let's look at the algorithm more formally. So here you have this input set S, this B tree T, and also you have the parameter B here, and this is the query range. Okay. So again, we assume that Q1 has a successor. Okay. So again, I don't want to describe this tedious corner case, and I'll leave that to you. So what's the query algorithm? The query algorithm says, okay, you first find the successor. You always start from there, okay, and you keep visiting the next leaf, okay, until you can figure out, you don't have to do it any further, okay. So basically, this happens when you have seen an integer that is outside the range. This Q1, Q2. This is already exceeding Q2, so you don't have to go any further, or you can see that all the leaves have been exhausted. Okay, all the leaves have been exhausted. This means you have access to everything. Okay, now here is a theorem. It tells you in general how efficient this range query is. So the query cost complexity. I use the word complexity. I don't know if you can understand it. So basically, this query complexity says big O. Okay. Now remember, there was a hidden constant here, and also this big O gets translated to an upper bound, right? Anyway, so this query complexity is log base B of n plus another term. Okay, so what is this k? K is how many integers you are reporting. Okay. Well, k can be very large and k can be very small, right? So k can go anywhere from 0 to n. Okay. So this is the bound. Now, basically, this log base B of n is the height of the tree, right? And this k over b basically says, how many leaves do you have to travel? Okay, so you can definitely find everything you want to report within k over b leaf nodes. Okay, so that's the theorem. Okay, an interesting remark here. So in this algorithm, in this example, I've been using this B plus tree with the pointers. Okay. Now, an interesting question for you to think about is, what if I have just an ordinary B tree without the pointers? In that case, would I be able to still achieve this guarantee? Okay. Well, the answer is yes. In fact, as a hint, all you have to do is to access a little bit more internal nodes. Actually, in this example, for instance, if you don't have the pointers, and then you will also have to access U3. Okay, but I will leave the details to you. Okay, nice. So far, we have talked about how to use a B tree to answer queries. And next, we're going to talk about how to update a B tree. Okay. Well, you already know there are two variations of the B tree. You can have B tree or B plus tree. And our discussion will focus on, just the B tree. I would not talk about B plus tree explicitly unless it's not, totally, completely, entirely straightforward. Okay. So before we can talk about insertions and deletions, we will first have to talk about two primitive operations. So these primitive operations are important because they will allow you to perform insertions and deletions easily. Okay, without understanding these operations, the insertion deletions will appear to be quite complicated, but they don't have to be. Okay, and um, the key is to take out two primitive operations and understand them early. Okay, so this is exactly what I'm doing here. Okay, so let's start with the split algorithm. Um, So here we need a new concept. This concept is overflow. So as you know, we have this B. This B puts an upper bound on how many elements you can fit into one node. Sometimes, during the update operations, insertions and deletions, we might temporarily have a node that contains more than B elements. In this case, we say that the node overflows. All right. And this is not a situation we can accept because it violates the basic definition of the B tree. And so we have to handle it. And the weapon we use to handle an overflow situation is the split algorithm. So the split algorithm here is described formally with the pseudocode. But as usual, I think it's a good idea to look at an example first. So say in this situation, we've got a tree here. And as you can see, this U overflows. The capacity is 3, but now we have 4 routing elements there. Okay. And what you do in this case is pretty intuitive and straightforward. You like to create 2 nodes, and you like to distribute the elements inside U, these 4 elements, evenly into the 2 new nodes. And in doing so, you would like to respect the ordering. So you see the 2 smallest entries of U get assigned to U1, and U2 get the 2 largest entries. Okay. So always bear in mind that every routing element comes with a pointer, right? Because this routing element has a child node associated with it. And the address of this child node is, excuse me, stored as a pointer together with this routing element. So when you reassign the routing elements, you also move the corresponding pointers accordingly. Okay. Now, this is what it looks like after the split. As you can see, 2 child nodes of U are now assigned to U2, and the other 2 are assigned to U1. Okay. Now, one more thing. Every node, if this is not the root, every node will have to have a parent. So you see this U has this parent P, and P contains a routing element for U. Okay. So here we've got U1 and U2. As you can see, one more node is being created, and this node would have to get included into the tree. We have to get connected into the tree. And the way to do it is to insert a new routing element into the parent, and also a pointer. So this pointer gets this node U2 connected into the tree. So what can be this routing element? Basically, there's only one option. We don't really have a choice here because we have a very stringent but clear definition about the routing element. It will have to be the smallest inside the node U2. So that's why 67 goes up there. Okay. So this is a split situation. And by the way, just a heads up for you. So this new entry into the parent P could also cause P to overflow, right? But this is going to be taken care of by another split operation. So one split operation handles one overflow situation. So this is going to be handled by another split, which is performed the same way. Okay. All right, now let's talk about the I/O cost of a split. So as you can see, you will have to write at most 3 nodes, right? You have to write U1, you have to write U2, and also you have to update the block of P. So that counts as 3 write IOs. And also you have to read these 3 nodes, maybe not U2, but you have to read P, you have to read U1. Anyway, we don't want to be bothered with a constant, maybe 5 or 6. In any case, you can say this split operation performs a constant number of IOs. Okay. If you want a precise number, I think it's normally 4. Um, and it can also be 5 or 6, but it's not so important. Okay. So that's the split operation illustrated with an example. Now let's go back to the formal definition, formal description. Let's see how the split algorithm works in general. Well, you need to have a node that's currently overflowing. So let's say this node is U. Okay. So then this split operation is going to operate on that. So here comes something that might look a little mysterious to you, because you would assume that we whenever we handle an overflow, and then this node is going to have exactly one more than what is allowed, right? So the number of elements there is going to be b plus 1. On the other hand, if you look at the description here, I'm saying something more general. I'm saying, okay, so you can give me a node, and this node contains more than b elements. Let's say t is the number of elements in the node, and this t is more than b for sure. But I also allow more choices for this t, more possibilities for this t. So this t can go up to 1.5p. Okay, so say this is a node, and the split operation will perform the same way. So if you think about it, this is a good thing, because the exactly the same procedure is applicable not only to a node strictly with b plus 1 elements, but also it's applicable even if this node contains a little bit more than that. Okay. This is going to be useful later. We'll see this. We'll see why very shortly. This is going to be useful when we talk about the merge operation, which handles the opposite of overflow. Okay, the underflow situation. Okay. Well, anyway, the procedure in terms of the procedure, in terms of the steps, we don't have to be bothered by that. In any case, you have a node containing a bunch of elements, and we're going to split those elements into 2 nodes. One is called U1, and the other one is called U2. Okay, and you want to distribute the elements by respecting the ordering. So you get this t, and you divide this t by 2. So you allocate half of the elements to U1, but these elements will have to be the smallest half. And then U2 contains the remaining elements. Good. All right, so once this is done, and then you have this P, so this is the parent node, this is U, right? So now this has been split, so you no longer require U anymore. So this U is gone, okay? So that's why you are removing it, okay? Now if this U has a parent, and then you have to make both U1 and U2 the child node, 2 child nodes of P. Okay, so this means you have to take care of the wrapping elements as well. Well, there is one possibility. It's possible that U itself is the root. So in this case, you don't have a parent. Okay, so this is basically this node U, and it gets split into 2 nodes, U1 and U2, right? So if U has no parent, what does that mean? It means that U is the root of the entire tree. But now the root gets split. Okay, and then that's the moment when the height of the tree increases by 1, right? So in this case, you will have to create a new root, right? So let's say this is the new root, and this new root would have U1 and U2 as the child nodes. Okay. So this is the split algorithm. This is a fairly, I would say, fairly intuitive algorithm, right? So if you imagine you being the designer of this algorithm, I guess sooner or later you will arrive at something similar. Okay. Okay, so basically, the key here is to distribute the elements evenly into two new nodes, but you have to respect the ordering. Okay, and also remember to take care of the routing elements, and that's pretty much it. Okay. Well, here there is a remark that I'd like to point out. As I said, what I'm describing here should be applicable to both the B tree and B plus tree, even though I use the B tree as the example in the discussion. Uh, I would insert a remark at those places where it's not entirely straightforward to go from the B tree to B plus tree. Well, in fact, this is one of those places. I think this is the only place, as you will see. So here, if you are splitting a leaf, okay, so here we're not splitting a leaf, but if you are splitting a leaf, and then you have to remember, this U2 will become the next leaf, the leaf in the total order next to U1, right? So in that case, what you have to do is, you have to keep a pointer from U1 to U2, that's pretty easy stuff, right? So I'm pretty sure you can figure this out even by yourself. Okay. All right, so that was split. And now we're gonna talk about the opposite of split. That's about merging. Okay, so if you think about it, split is the operation that creates new nodes. So that's how the tree gets more and more nodes in general. But we may also have to reduce the number of nodes, right? You can imagine as we keep removing elements from the tree, and then the tree gets smaller and smaller, right? The operation that removes nodes is the merge. This is something we're going to talk about right now. But the thing is, in order to talk about merges, we need one more concept, and this is the concept of sibling. Okay, sibling. Actually, a pretty standard concept in tree terminology. Nevertheless, let's look at it again in the B tree context. Okay, so you think about U1, for example. So U1 has two child nodes, right? So, these children, what do they call each other? Siblings, right? And also there is an ordering over these two channels. U2 is to the left of U3, right? Because its routing elements are smaller than those in U3. So in this case, we say U2 is the left sibling of U3, and conversely, U3 is the right sibling of U2. Okay. The same thing goes for every internal node. Let's say U3, three children, Z3, Z4, Z5. And if I say, okay, who is the right sibling of Z4? And then should tell me that's Z5, okay? And who is the left sibling of Z4? Z3, okay? Who is the right sibling of Z3? Well, there's only one, okay? Z4 is the right sibling. Z5 is not the right sibling of Z3, okay? So when I say right sibling, I mean really just one, okay? The next right sibling. Okay, so here we are, the merge algorithm. So again, the pseudocode here, we will look at the pseudocode, we'll look at the formal description after seeing the basic ideas from an example. However, we need a concept again. This is to the opposite of overflow, right? Now this is saying overflow, okay? So remember, this B also gives you a bound on at least how many elements you need to have in this node, right? Typically, the answer is B over 2, okay, B over 2. And therefore, if you go below that threshold by 1, and then you have an underflow situation, okay? But I also mentioned previously that the only exception for the lower bound happens to the root. Okay, so the root is allowed to contain, less than b by 2 elements. However, it will have to have at least 2 elements. Okay. If this is not true, and then it means the root contains only one element, and in that case, we say that the root underflows. Okay. So this is this looks actually a little complicated, but it's in fact fairly intuitive. Think about what happens, right? Let's say you have the root, but then you have just one child, right? And then this child this child node has some subtrace. But then a question comes up, right? So why do you need the root in that case, right? If you have just one child, why don't you just forget about the root, right? And use the child node as the root directly, right? And then you get to save some space. Why not, right? So this is pretty much the idea, okay? So this is why if you have just one element left in the root and you have a child node, you might as well just remove the root, okay? So let's look at an example right away. So this example is going to illustrate the main ideas, right? So now let's say B is 3. So every node is supposed to have at least B by 2, that's 1.5, and you have to bump it up to 2. Okay, so every node needs to have at least 2 elements. Now we have U2. Now U2 has just 1 element, so that's no good. Okay, so we have to handle this underflow situation. The merge operation says, okay, grab a sibling. Okay, grab a sibling. It doesn't matter which sibling. If you have 2 siblings, a left sibling, a right sibling, it doesn't matter which one you grab, but you have to grab one of them. Okay, so in this case, U2 has a left sibling but no right sibling, so you don't really have a choice. So you grab it, and then you merge, right? So when you merge, you just simply combine. All the elements together. So this is giving you just one node, okay? So in this case, you lose a node. So this U2 is no longer there, U1 is still there. And you therefore have to remove one routing element from the parent as well. So the 67, before it was here, but now, this U2 no longer exists, and therefore, one entry will have to get removed from the parent. So once again, you have to remember routing elements always come with pointers. So when you move a routing element, you also have to move the pointer as well. Okay, so this is the first example, but there's another example. Now this example illustrates a slightly more complicated situation that could happen. So once again, B is 3 and U2 currently underflows, okay? So as I said, you have to perform a merge. And for that purpose, you have to find a sibling, and in this case, U1 is the only sibling. So you do what you are supposed to do. So now you've got a node with all the elements in both U1 and U2. All right, so what do you see? Now this is something maybe somewhat unexpected, right? So you can see the merge actually creates an issue for U1, okay? Now U1 contains more than B elements, okay? So this can really happen. As you can see, U1 before the merge, it contained 3 elements, which is okay. This is allowed, this is in the normal range, right? But after taking the element of U2, now U1 overflows, okay? So indeed, this is something that can really happen, but you already know how to handle an overflow, right? So you see, this is the benefit of extracting the primitive operations, right? So we know how to handle an overflow. So at this moment, I don't have to repeat the explanation. So all I need to say is, just go ahead and handle the overflow the way you already know. So this requires a split. Okay, so there's no mystery more than that. There's no more mystery than that. So you got the merged node, which overflows. So you split it. Okay, you split it into two, and then you also take care of the routing element in the parent. Okay, so if you understand the principle, there's no confusion possible. You have to be able to explain every single detail that is happening in this example. For example, why did you lose this ADA? You lose this ADA when you perform the merge, okay? Because this ADA was supposed to be U2, but now it's gone, okay? And on the other hand, why do you have another routing element here, 67? And how come you've got another U2 here? Well, this U2 is actually the product of a split, all right? So this 67 is now the smallest routing element inside U2. Okay, you see, everything should be perfectly clear. All right, back to the formal description. I want to emphasize, no matter how many examples you have seen, the examples, you have to remember the examples should not replace the formal description. Okay, because examples are like special cases, right? But on the other hand, if you look at the formal description, it's supposed to be an algorithm that can be applied in all the possible situations. Okay. So that's why I come back to that's why I come back to the slide to talk about this algorithm in general. So you have two nodes given to the merge operation, and between the two nodes, only one of them is underflowing. Only one of them. Okay, not both. All right, one node will have to be healthy. Okay, the other node is having trouble. And furthermore, these two nodes would have to be siblings of each other and without loss of generality. Let's say U1 is the left sibling of U2. Okay. And then what you do is you have this situation, P, U1, U2. Remember, you may have some other child nodes for P, but then what you want to do is you want to combine them, combine this U1, U2 into one node. Okay, so basically you move all the elements in U2 into U1, and after that you can just delete U2. Okay, but then in this case you have to remember to take care of the routing element. You will have to get rid of the routing element in the parent P. Okay, so after this, and then you have to see whether this U1 is currently okay. It may not be. It may not be if U1 it has too many elements. So there's a possibility that U1 could overflow, and in that case, you simply split it. Okay. Well, here I can talk a little bit about this mysterious range that you saw before. You can see here we need to design the split algorithm to handle a node that has not just B plus 1 elements, but could have more elements up to 1.5B. So why is that the case? Well, you think about it, right? So just do a little bit of analysis. How many elements can this U1 have after the merge, right? So you can see before the merge, U1 was healthy, right? So it can have anywhere from B over 2 to B, okay? On the other hand, U2 is not healthy. So U2 will be having, slightly one less than what is compulsory, right? So this is the number of elements inside B2 at this moment. Okay. Sorry, did I say B2? I should have said this is the number of elements inside U2 at this moment. Okay. So if you look at U1, you can see that U1 will have at least B over 2 plus so many elements. So this is the smallest element that you can have. But how many elements can you have? At most, you can have B plus so many elements, right? So that would be the case when U1 before the merge had B elements, and that's the maximum possible, right? So if you look at this, this is less than B 1.5. Okay, I won't prove it here, but you can figure this out on your own. So this means when we handle a split, we'll have to be prepared for the worst case situation where the node that requires the split can have up to say 1.5 B elements. Okay, so we need to have an algorithm to take care of all these situations. Okay, so that's nice, right? Now, this is another useful lemma. Just like split, a merge can be performed in a constant number of IOs. Okay, so basically this is not surprising at all, right? Because how many nodes are we touching, basically? We're touching U1, touching U2, and also we're touching the parent. So all in all, we perform a constant number, right? You only have 3 nodes. And for every node, you just basically read it once and write it once. So that already tells you the number of IOs cannot be more than 6. Okay, so that's a constant. Okay, good. So now we know the 2 primitive operations, split and merge. So next, I'm going to talk about how to insert a new element into the B tree. And we will have overflow situations, and then those situations will be handled by splits. Okay, and you will also see that one single insertion can trigger a lot of split operations. However, we're able to say that there is a log-based B of n upper bound on the total number of IOs we perform in any case. So this is the insertion algorithm. So once again, let's jump into an example right away. So here, this is the input set. Okay, remember 1-1 correspondence between data elements and the numbers in the set. So here we are inserting 60. Okay, 60. So how do you insert 60? 60 will have to go in here. Okay, so how do you find this node? Well, this is pretty easy. You can find this node using, predecessor search. Okay, anyway, so you look for the predecessor, so 60, the predecessor is 49, so you find this node, and you would like to insert 60 in the same node as the predecessor. Okay, can you do successor? Definitely. Okay, so these two are symmetric, but I'll go with predecessor here. Okay. Anyway, so 60 goes inside, okay? And now, unfortunately, we have an overflow situation. As you can see, Z3 has 4 elements, so it needs a split. So you just split it, okay? So create a new node, and also some routing element will have to get added into the parent. So that's exactly what's happening here. We just performed the split, and this 60 is the smallest element in the leaf Z6. So we have to duplicate this routing element into the parent. But hey, as you can see, the parent now overflows. So we have to perform another split. You already know how to handle that. So you perform the split. So now this 81 will have to go into the parent. Okay, so that gives one more entry to the root. Well, the root is fine, on the other hand, 3 elements only. So this is normal. This is in the normal range. That's fine. So the insertion stops here. Okay. All right, now let's look at the insertion algorithm. You already get the idea, right? So the insertion algorithm says you first find the leaf that you want to store the new integer in. Okay, so you can find the leaf using predecessor search. Okay, um, so you let's say the node is z. You still remember how to find this z, right? So you have to descend a path from the root to this leaf z. Okay, so you already pay a number of IOs that's equivalent to the um, height of the tree, the number of levels in the tree. Okay. All right. So you put this new element into the node. So there's a little bit of assumption again. This assumption comes up again. So here we assume that the predecessor exists, but what if it does not, right? So this is something that I would leave to you to think about. Okay. So now you add the node you add the number to this leaf, okay, and then you have to worry about overflows, okay. So you check this node, say U is the node that you are checking at the moment. So if this Z itself does not overflow, and then all is good, and that's the end of the insertion. There's no more hassle for you, okay. On the other hand, if U does overflow, and then you have to split it, how? Well, we already talked about this. This is just a primitive operation. So you do that, and also you do what you have to do, right? So this will create one more routing element into the parent. And then you have to check the parent, right? Which is why you want to set this U to the parent, and then you check the parent to see if it overflows, and then basically you repeat from line 3. So you are at the parent now, and you check whether it overflows. If not, all good, and this is the end of the insertion. Otherwise, you split the parent, and then you have to, check the parent of the parent again, and etc. etc. So that's the insertion algorithm, and here we've got a very useful theorem. So the theorem says every insertion can be performed in log base B of n IOs. Okay, so once again, that is the height of the tree. So why is this? I told you before that the predecessor search itself is obviously log base B of n, no problem. But there is a propagating process in the worst case, right? Because you have to split at the leaf level, and then you have to perform another split at the parent level, and maybe in the worst case, you have to perform a split at every single level, and it's possible that you might even have to increase the height of the tree by 1, right? But the thing is, how many overflows do you have? You have the same number of overflows as the height of the original tree, right? So that's log base B of n. And we said earlier that every split operation can be handled with a constant number of IOs, and therefore it's just log base B of n times a constant. Okay, so once again, the constant has nothing to do with n and b. The constant will be 6, something like 6, right? I told you about that. So all in all, you will be performing log base B of n times, let's say 7, something like that, right? But that's just a big O of log base B of n, right? So in computer science, we don't really bother too much with the constant. We worry about, how the cost would scale with respect to the parameters n and b, right? But the constant here will have to be reasonably small. And also the constant here must not depend on n and b, right? So no matter what these values are, the constant will always have to be the same, okay? So if you think about it, this is sort of like focusing on the most important growth of the cost. So we're talking about how fast, the cost will grow. So the constant is not something that will affect the growth, right? But this n and b, they will be affecting. They are the parameters we are concerned with. Okay? And furthermore, this big O is not saying that the insertion will definitely be performing, let's say 7 times log base B of n, because you have this big O should be understood as less than or equal to, some constant times log base B of n. So finally, we look at deletion. This is the formal algorithm. Let's skip it for now. Say we have this B tree here, and currently this is a very nice tree and no issues with it. We want to remove this 44. Okay, now remember, when you delete something, you have to, when you delete something, you have to provide um, the integer that you want to delete. Okay, so you delete it. I'm sorry, you say, here's the integer and please delete it. Okay, so the deletion algorithm starts by finding this element. Well, fair enough, right? You have to find it. So how do you find it? Well, predecessor search, right? Still remember the definition of predecessor? I said, say 44 is in the set. So in that case, the predecessor of 44 is just itself, right? So predecessor search is actually good for finding the element as well. Okay, so not just for finding the element that's before it, but it's also good for finding the element itself. Anyway, so you use predecessor search and then you get this 44. You just get it removed. Okay, so once you remove it, and then this Z1 will lose an element, right? So when after that, you look at this element, you look at this null, and you can see it underflows, right? Forgot to mention, B is 3 here. So this is what you do, and therefore you have to perform a merge. So you have to merge Z1 and Z2, right? So this is an underflow situation. So the merge node is shown here. So this is fine. But remember, since you are losing a node, you're losing a leaf here, you also have to remove this routing element from the, actually you have to remove this routing element and change, oops, what happened? Sorry, where am I? Okay, sorry about that. I don't know why that happened. Maybe I touched something. Anyway, so we're back here. As you can see, this node is gone. So, this node is merged into Z2, right? Z1 is merged into Z2. So this routing element is gone, but this routing element will have to be updated to 49, right? So that's what you see here. Why do we have to update it? Because this 49 is supposed to be always the smallest element in the child. Okay, so it's 49 here. And you can see this 44 is lost. And so this node has only one element left, which is not okay, right? So this is an underflow situation, and it needs to be handled. Okay, so how do you handle the underflow situation? You find a sibling, and then you have to merge the two. Okay, so you do just that. Now you get a node with 3 elements, but remember you are losing a node. So this routing element from in the root, it is 81, will have to get removed, right? By the way, as you can see, this 49 also gets updated. Before it was 44, 44 was here. 44 is exactly the node, the element that you're trying to delete, right? So before it was 44, before it was correct, but now after the deletion, this is no longer correct, right? However, when you get back to the root, you have a chance to fix it, because you from U1 and then you look at U2. Yes, this is the time that this 49 will have to get updated. Right? You see it right here. And so you do that, but then the root contains only one element. Now this is a situation we talked about before. It doesn't make sense to keep the root anymore. You could as well just use the child of the root to serve as the new root. So now the whole the height of the tree decreases by 1. Okay, so it doesn't sound too difficult, does it? Once you understand the principle, I think this is very difficult to forget, right? I would say this algorithm would probably stay with you for the rest of your life, provided you understand the principle. Okay, not just memorizing the the steps. Anyway, so let's look at the deletion algorithm formally. So this is the integer that you try to remove. Okay, so you remove it. Sorry, you have to find it first. I forgot that. You have to find it through predecessor search. You find it, and then you remove it. Okay. Now you check whether the current node underflows. If it does, if it does not underflow, all is good. And this is the end of the deletion. Okay. On the other hand, if it does underflow, and then you have to merge it with a sibling. Okay. And if so, there is a chance that the parent might underflow now. So that's why you have to go back to the parent and check again. Okay. So this can propagate all the way back to the root, as I demonstrated with this example. In that case, if you are really, really standing at the root and the root underflows, and then you will remove the root and use the child of the root to serve as the new root. Okay, so in this case, T loses a level. Okay, now let's look at this theorem. This theorem says a deletion also can be finished in log-based B of n IOs. Essentially, we have proved this because you first perform a predecessor search that takes log-based B of n, right? And then you have to perform merges, but only one merge at each level, and every merge can be done in constant IOs, and you have log-based B of n levels, and therefore, the total deletion time is log-based B of n. Okay, once again, this is big O. All right, so this is the last slide of today's lecture. It's been a long lecture. So I hope you have understood the principles behind the B tree. Once you have fully understood the principles, you will be able to answer these questions. Okay. So I'm not going to discuss the answers now in this video, except to say that they are very good tests for you to test if you have a solid and accurate understanding of the B tree. So the first question says, currently we assume that the input set is a set of integers. Okay. However, I can tell you the B tree is a comparison-based data structure, comparison-based. Okay. It doesn't really matter whether the elements are integers or they are strings. Strings just like names, right? People's names. As long as these elements can be compared according to some total order. For example, if we're talking about names, okay, strings, and then you can order the names alphabetically, right? So that would be a total order. So you're able to build a B tree over the names, and then you can also do predecessor search, range queries there, no problem. Okay. So think about why this is true, and think about whether you would have to change a lot of things to make that happen. Okay, so that's one thing I want you to think about. And another thing I want you to think about is this. Okay, currently we assume that the input is a set. All right, this is set. Well, this set contains more information than it seems. This set itself basically says that you don't have duplicate elements in the set. Okay, this set is a mathematical concept taught in discrete mathematics, right? If you have duplicates and then it's not a set, people usually call it a multiset. So what I'm saying is, what if this S is a multiset? Okay, what if it contains duplicate elements? Okay, the same integer might appear multiple times. So in that case, if you want to create a B tree on such a multiset, I mean, what changes would you have to be doing? And also, what would be the answer of predecessor search, and what would be the answer of range query, and how would you be able to support those operations? All these things require some thinking, okay, but they are not too difficult, okay. All right. Thank you very much for listening, and I look forward to seeing you in the classroom.